Alright, so on part 2 now. So here in our example, I want you to actually find the maximum and minimum of f on the interval -3 to 1, including -3 and including 1. So first you're going to need to find the critical values, and now you're going to actually have to test those values to find what is the actual minimum and maximum. Also, unless it's specified, and because this is a closed interval, we're referring to absolute minimums and maximums. So find the absolute minimum and absolute maximum. So pause the video, unpause when you're ready to check your work. Okay, so here you should get that -230 is the absolute max and 1 -24 is the absolute min. So how do we come up with that? Well, first we want to recognize, although this is a polynomial which has a domain of all real numbers, we are restricted to -3 to 1. So we are using the closed interval -3 to 1 as our domain. So now I find the derivative. The derivative is 3x squared minus 6x minus 24. Set that equal to 0, and I can divide by 3 because everything has a factor of 3. And then this factors into x minus 4 times x plus 2. Set each factor equal to 0. And I get critical values of x equals 4 and x equals -2. So those are my critical values, but notice that 4 is not within my domain, so I'm just going to ignore that value. Now I'm going to use the critical value of -2 as well as the two endpoints to see which is the highest and lowest points. So f of 3 is 20, f of -2 is 30, and f of 1 is -24. So therefore the value of -230 is my maximum, and +1, -24 is the minimum. Next one. Same thing, I want you to find the absolute maximum and minimum on the interval -1 to 3 for the function f of x equals 2x minus 3x to the 2/3. Pause the video, unpause when you're ready to check your work. Alright, so here we should end up with the point -1, -5 is the absolute minimum, and the point 0, 0 is the absolute maximum. So let's see how we got that. First, again, we want to recognize we're using a closed interval from -1 to 3, including the -1 and the 3. So now I want to find the derivative. So the derivative is 2 minus 2x to the -1/3, which is 2 minus 2 over the cube root of x. Now, I would recommend, highly recommend, so that you don't miss critical values, that you take this form of the derivative here and get a common denominator like I did here in the blue. If you don't do that, there's a good chance that you are going to lose out on critical values. So I got a common denominator, set the derivative equal to 0, numerator equal to 0, and denominator separately to find where the derivative equals 0 and where the derivative does not exist. This gives me critical values of x equals 1 and x equals 0. So these are my critical values. Both of those are within my domain. So now I need to actually test the endpoints, so -1 and 3, and the critical values 1 and 0. So when I plug in -1 to the function, I get -5. When I plug in 1, I get -1. When I plug in 0, I get 0. And when I plug in 3, I get approximately -0.24. So the highest value is 0. The lowest value is -5. Alright, so in conclusion, we want to make sure we understand how to find critical values. They are essential to finding maximums and minimums, which is what we're going to be spending a lot of time doing. It'll also be essential in finding inflection points, which is what we're going to get to in a couple of days. That's using the second derivative. So critical values are inputs where the derivative is 0 or where it does not exist. So we find the derivative, we set it equal to 0, and set the denominator equal to 0 as well, because that's where it will not exist. They are the potential locations of extrema, which are maximums or minimums, also sometimes referred to as turning points as well.